Located in Zealand, ODL is a manufacturer of door glass, door frames, and blinds for doors and windows. Their products provide solutions for style, safety, energy efficiency, and privacy. This includes decorative glass and blinds between glass. This year, ODL is celebrating 75 years of innovation in creating products that improve people's lives. Tighter home designs reduce available airflow through windows. Using the front door is an option to provide additional airflow. Current designs include vents, which are difficult to meet airflow expectations, while other designs do meet requirements, but they have a utilitarian look. ODL challenged the team to develop a looks-like, works-like prototype that provides adequate airflow without compromising the aesthetic appeal of the home.
Key specifications include using a 1-inch thick insulated glass unit and a 23 by 65 inch door cutout, an airflow equivalent to a 3 foot by 5 foot window with a 3 foot by 2.25 inch opening, closed with less than or equal to 10 pounds of force, and shall not close when subjected to forces less than 1.5 pounds, and a person of average height cannot reach within the prototype and access the doorknob.
The prototype's design utilizes a tilting motion of the insulated glass unit, otherwise known as IG. The tilt motion creates a 3-inch opening by rotating the IG about a hinge at the base of the door cutout. The IG opens into the home to ensure that in the case of precipitation, water will not enter the home. The IG and linkages are attached to both the frame and inner walls of the door cutout to help support and restrict this tilt motion. When the IG is fully in the open position, latches move to engage a peg with a lock on either side of the door. The IG can be placed back into the closed position by unlocking the latch and moving the pegs outward and gently pushing the frame back into the original position. The locks will re-engage at this point, creating a secure closed state. 2 sets of flat plastic frames are used to create a sleek appearance. The interface of these 2 frames also provide a water and airtight seal. The outer frame set is attached to the door, while the inner frame set is attached to the IG. This provides enough support to operate the system while still maintaining an acceptable appearance. There is a screen incorporated into the outer frame that runs across the entirety of the door cutout, reducing bug infiltration into the home.
Static calculations were conducted to understand what forces would be acting on internal components. The free body diagram shown displays the reaction forces at the bottom hinges, the weight of the IG, and the force experienced by the linkages. We made the following assumptions for our calculations. The linkages experience forces in the Y and Z directions. 2 of the bottom 3 hinges experience loads. And finally, forces and reactions are mirrored about the center of the door. Forces and moments about point A were calculated in all 3 directions. These values helped us further improve our design to make sure there would be no failures during use.
The team also conducted static analysis simulating an impact test to improve and verify the prototype's design. This test method uses a door laying horizontally on the floor and dropping a sandbag onto the center of the glass. The diagram on the left illustrates the key points of the metal components. The free body diagram on the top right illustrates the reaction forces produced by the sliding pin, linkage arm, and locking mechanism. Calculating the reaction forces for these components verified that the prototype will remain closed if someone attempted to break into the home through the front door. The free body diagram on the bottom right illustrates the reaction forces felt at the sliding pin and bottom hinges when subjected to impact loads. Again, these calculations were run to verify the design was strong enough to withstand non-standard loads.
To comply with specifications that the prototype will have an equivalent airflow as a 3 foot by 2¼ inch opening, preliminary airflow calculations were completed. In these calculations, the assumptions of constant density and flow driven only from pressure were made. Constant density was assumed to neglect relative local pressure changes from constricted openings, while flow driven by pressure was assumed as flow driven by velocity created too many unknowns to solve equations. For the double hung window, the volumetric flow rate was found through Bernoulli's equation as a function of pressure differential between the inside and outside of the home. Through the prototype's design, the area around the perimeter of the tilting glass insert was found to be 126 square inches or 0.876 square feet. With this area, Bernoulli's equation, and the discharge coefficient of the hopper-style window from ASHRAE, the volumetric flow rate was calculated for the prototype as a function of the pressure differential between the inside and the outside of the home. Comparing the double-hung window's airflow to that of the design prototype, it was found that over the same pressure differential and air density, the prototype would provide approximately 3% less airflow than that of the double-hung window. This discrepancy fits within the allowable tolerances under the specification. To comply with thermal bridging and overall U-factor specifications of the prototype, which does not include the steel or fiberglass door or IG insert, a thermal circuit was created from the prototype's cross-section for analysis. From the thermal circuit and material thicknesses and properties, the overall U-factor of the prototype was calculated and fits below the maximum specified limit. To determine the amount of thermal bridging of the prototype without the IG insert to that with the IG insert, the thermal resistances were calculated from the circuit. These resistances were then theoretically compared over the same temperature differential and showed that the prototype approximately contained 1.89% of thermal bridging. This amount fits under the maximum specification.
A computational fluid dynamic, or CFD, analysis was run to compare the airflow through the prototype and the airflow through a 3 foot by 5 foot double hung window with a 3 foot by 2.25 inch opening. Based on research, an initial air velocity was set as 6.5 feet per second. The mesh settings were kept the same between the two models, so that the only difference between the models was the geometry of the opening. Based on the information found in the velocity contour plots, the percent difference between the volumetric flow rates for the two models was calculated. Based on this calculation, it was determined that when a 6.5 foot per second initial airflow is present, the prototype will see a 10% greater airflow rate than the window. The results from the CFD analysis provide further evidence that the prototype will meet the airflow specification requirements. As a result of the ongoing COVID-19 pandemic, there were several modifications that needed to be made to the project. One of these modifications was to the amount of testing that was able to be conducted on the prototype. While some of the testing, such as determining the force to open the prototype and ensuring inaccessibility of the door handle through the prototype opening, were able to be done, testing that required external testing facilities became optional due to the inaccessibility and time restrictions for these facilities. Most notably, this meant that air infiltration testing became an optional requirement for the prototype. Another change to the project as a result of the pandemic was due to the inability of the team to create some of the components for the prototype due to the inaccessibility of Grand Valley's machine shops. This resulted in using a third-party, Skylark Machine and Automation, to create the custom components.
The team achieved a clean look by painting the plastic frames and door white, making the overall transition from door to frame seamless. Painting the internal components black reduced the visibility of any imperfections on the surface of the metal.
The knobs used to open and close the prototype were placed at a height of 54 inches from the floor. The knobs themselves were designed to fit comfortably in the user's hand and have a minimal appearance on the surface. Both the position and the knob design allow the average person to easily operate the prototype.
The IG was able to tilt outward and allow airflow through the opening, while the screen prevented bug infiltration and theft. This perceivable airflow further supports our theoretical airflow verification of our design.
Due to the COVID-19 shutdown and restrictions, the project's finalized design and documentation were completed through online meetings and collaborative softwares. These included Microsoft Teams, Google Hangouts, and GrabCAD. Virtual meetings helped our team to communicate on a regular basis while sharing solutions on how to navigate the project during COVID obstacles. From Grand Valley shutdown, the team was unable to use most university shops, spaces, and equipment. Therefore, we were required to search and communicate with vendors to ensure that manufactured project components met the team's specifications.
We would like to thank Skylark Machine and Automation for their donation of labor as well as their ability to work with us on short notice.
We also want to thank the Schmidt family for allowing us to use their home, tools, and assistance to build our prototype.